So some of the non-idealities of the direct conversion architecture are have to do with carrier leakage. And we note here that the in-phase and quadrature data at the baseband are directly shifted to the carrier frequency. So as you know, this signal gets up converted right to there. The carriers are generated by the local oscillator, as we mentioned. But in practice, typically this local oscillator should only drive the mixer, but there's going to be a small amount of feed through the two mixers. And if you're wondering how could I possibly leak through the summation devices, this is actually because the local oscillator is generally in a circuit with the other components. So there's either a parasitic coupling or it's going through an actual component such as the mixers. And we end up with it leaking out and it popping right down there on top of our signal. And so this is one of the challenges or downsides of direct architectures, is trying to handle the LO that leaks through. So let's understand a little bit how this affects the signal and the constellation. So what I've written here is simply the signal for the I and the Q signal, and this is our in-phase LO and our out-of-phase LO, our quadrature LO. And remember, I and Q are just chosen arbitrary. All we need is that I and Q are 90 degrees out of phase, so that when they're transmitted, they're orthogonal to one another and can be received independent of one another. So now what happens if a certain amount of carrier leaks to the output? And so what we've done here is we've just added some factor K of our carrier and a small phase difference. So here we have our Q modulated signal, our I modulated signal, and this is just a single tone of the oscillator. And so now I'm just going to break this out of using an identity for cosine of U plus V. If you look at that identity, you'll find it'll give you a product of two cosines and a product of two sines. And so K goes out in front of both. And what you notice is that cosine of phi term here and the sine of phi term here. Typically phi might be fixed, and so this is just going to be a constant. That's not always the case, but you can see here that it's a constant and K is a constant. So what we're going to do is add a little bit of a constant carrier frequency to our final signal. And we then can show that it puts into both of the in-phase signal here and then the quadrature signal here. Both have this non-ideality of the distortion that's been put in. So basically what we're doing is we put a DC offset into the I and Q if our carrier leaks through. And so let's just look at what happens to the constellation. So here's a 4-QAM constellation, and if we have a little bit of carrier leak through, that's going to add an offset to each signal, and it's just going to shift our constellation up in one direction. So that's going to be the effect of a carrier leak through that gives us this DC offset. You might be thinking, well, it's a DC offset, that's not a problem. However, if you imagine that you're a receiver, and what the receiver does is it says anything in this box is 1, 0. And so if your received symbol, if you will, marches out of that box, it's no longer going to receive the correct signal it should. Typically what will happen is we can actually shift these boxes. This is the received box so that it's centered around there. That's something we can do if we want to try to fix an offset that we know that's happened. But if we don't know the offset's there, we'll be looking right around here for the signal, and if it's not there, we could have an incorrect reception or an error.